Hi, and welcome to this lecture, which is section 4.2. What is Radon-Nikodym theorem about? Well, we've talked many times about that if I have a non-negative measure mu, I can, and whatever function f here, as long as it's measurable or integrable, or bigger than or equal to 0, and measurable, in either case, I get a new measure mu by this formula. But not all measures mu arise in this way if I start out with a given mu. The typical example is mu equal to the Lebesgue measure and mu being the Dirac measure, right? Because then you would have in fact, all I said is not necessary, it suffices to just consider this example, right? So then we have a 1 here, and here we have 0. And this example leads the way. So if I put here any set whose mu measure is 0, I'm going to get the 0 integral. So that's the property we're going to single out here. So we say that mu is absolutely continuous, and it's written like this, a double less than or equal to. If mu of a is 0 for all a such that mu of a is 0. And this, again, this is only interesting if mu is non-negative, because otherwise being 0 here doesn't say much if mu is not non-negative. But that this is 0 implies that this is 0, that says a lot. So Radon-Nikodym theorem basically says the opposite of what I just stated here as obvious, that if we have this form, then we have this. Radon-Nikodym says the other way around. But there are two versions of it. So we have to either discuss the case where this is a non-negative measure and when it's complex or finite sign. Finite sign is like a special case of complex. So we just discussed complex and non-negative. Starting with the latter. So if mu is bigger than 0, okay, mu is always bigger than 0, but let me write it. If these guys are sigma finite and mu is less than or absolutely continuous with respect to mu, then there exists a function f which is measurable, but I don't feel like writing that. In space X with values in 0 to plus infinity, such that the mu, well, let me write out the formula, mu of a is equal to integral over a f d mu. For some reason this function is called g here in my notes, and I have a slight feeling there's a point with that, so if you stick with that. That's the version 1. Radon-Nikodym version 2. Here both measures need to be finite, I believe. Right. So in the complex case, we just swap this piece for u is complex. And mu is still sigma finite, and we have the yada yada. And the conclusion is the same. The only thing is that then g is a function in L1. And then we have, at the end of the day, this formula here. The proof is not that long, but it is very nice. Note that, so if mu is a complex measure and we have all of this, then we can identify it as a sum of 4 measures that are all non-negative and apply the first part. So the second part here is really pretty obvious. But not obvious, but a consequence of the first part. So I'm just going to do the first part. And as usual, if you understand, if you have something, you need to assume sigma finiteness. If you do the finite case, the extension to sigma finite is just a boring technicality. So I'm not gonna do that either. So we do here now proof. Assuming u is bigger than or equal to 0 and u is finite. Well, also u is finite. U and u are finite. Well, then many nice points in this argument, but the first nice point is how on earth do you get this function g? I mean, how would you even begin to construct it? And the idea is very clever, so please pause the video at this point and just think about it. This is what you have to work with. Only this inequality here. How would you set this up so you get a measurable function out of some sort of process? Okay, answer comes now. Let S be the set of all f, which of course they are measurable, such that if you integrate f against mu, you are less than mu of a. Basically, if we know that there exists a g, such that we have this formula, then basically what I'm saying here is I'm just considering f to be, I mean, this set S is just all functions f which are less than g almost everywhere. So then somehow I should get my g by doing some sort of supremum process here in functions in S. Of course, it's better to deal with a sequence that's somehow convergent, because if I just do the supremum, you know, if we know f is less than or equal to g almost everywhere, at point-wise, this doesn't mean much, so we cannot really just do a supremum like that. But what we can do to get a sequence here is now we have our set S, and we set now L to be equal to the supremum of integral f d mu for all f in S. Okay? So again, this supremum L here should be basically just nu applied to the full space, right? Nu of x. But we don't know that yet. But what we're going to do is first we can take a sequence of functions f, k, such that the value here converges to this L. This is step one. And then if L is less than, you know, nu of x, at the end of the day, we're going to use some yada yada to get a contradiction. That yada yada is very beautiful and nice. But let's start with the construction of our function g, and then we do the yada yada in the end. Okay, so pick. Yeah. So now we would like to say that our function g is somehow the limit of fk's. Problem is we do not know really that the fk's are increasing, so we cannot say that the limit exists point-wise. So we have to deal with that somehow. But we deal with that in a very easy fashion. Let me put this one here. So this is my function f1. Here's my function f2. Then this function, it turns out it's also going to be in S. And yeah, then I can replace f1 and f2 by the maximum of these two. So this, and then if I have f3 here, you know, then I just repeat this. So I'm going to define a new sequence. Okay, so okay, so the first one, f1, that's going to be my g1, and then this one, that's going to be my g2, and then this, that's going to be my g3, and so on. So, yeah. So, let A equal to the set of points x such that f1 of x is less than f2 of x, right? So that would be like over here. And now we have, well, okay, let's call this b. So what I want to do now is I want to integrate the function which is the maximum of f1 and f2, which, well, okay, what I call g2, and I want to check that this is in S. So how do I do that? I integrate over some a against the mu, and I want to know if this is less than mu of a in my definition here. But this is, of course, then just integrating over a intersection b, the function f1. Sorry, here I want to have the complement. So where f1 is bigger, the mu plus integral a intersect b, f2, the mu, right? And now we use that, well, this is a new subset, so I'm in S, so I have this inequality. Okay, so then this guy, so max f1 comma f2 is a member of S, and then of course my G3, so this is my G2, okay, my G3 is going to be max f1 f2 f3, right? But I can think of that as max f1 f2, which I know is in S, comma another max here, right? So you just once you prove this for two functions, you do induction, and then you see that you can take max of any finite amount of functions, and you stay in S. All right, so now this is an increasing sequence of functions. So monotone convergence theory tells us that, well, I mean, we can define this pointwise, and then monotone convergence theory gives us what we want. If I integrate this over some set A, this is the same as doing the limit as k goes to infinity, integrating over that set A, and then gk the mu, but gk was in my set S, so this is less than or equal to mu of A, and here nothing depends on k, so this is just equal to mu of A. And that holds for all A. In particular, it holds for X. So we see that, okay, so this inequality says that G is also in S, and it says that L is less than or equal to mu of X. That maybe was, well, correct. That we knew already, now that I come to think of it. But anyways, so G is in S, and we have that inequality. So if we have equality here, then clearly G is somehow maximum in a sense. Yeah, here it gets a bit subtle. So now we have our candidate G, but how do we prove that this integrating against G gives us the same? And we need to, I mean, if we prove equality here, then we basically know only that integrating over X gives us the same, but we want to know that integrating over A gives us mu of A for any subset A in the sigma algebra. And this is where it gets tricky, right? So now suppose, so by the property in S, we know that we always have integral G over some A, the mu less than or equal to mu of A. So to get a contradiction here, we just assume that we have strict inequality for some A. So suppose this is very nice here, okay? Then So now if we integrate over all of x, then that will be integral over a plus integral over the complement. Okay, and this is now strictly less than u of a, and the other one is less than or equal to. So at the end of the day, I get strictly less than u of a plus mu of ac, which is equal to mu of x. So the fact that I have inequality on some subset A also tells me that my L is really less than my mu of x. All right, I messed up. We'll take it from here again. What do I do now? So I define the difference of these two. Typically now I want to show that this difference is 0. And note that this is, I mean, we still haven't used the fact that mu is absolutely continuous, right? So if this is the Dirac measure and this is Lebesgue measure, then my function g is going to be identically 0, and here I have a non-zero measure. Okay. But what we know is that if I plug in the big X here, then I get mu of x minus this integral, and we just established that that is a positive number. So this is bigger than or equal to some epsilon, right? And here is where the argument gets super clever. Then I subtract this epsilon. And I add here another integral where I integrate the function 1 against mu. So now I know that this is a measure still, but now this is a signed measure. So if I can add somehow the function 1 to my g, or epsilon times, okay, let's put the epsilon inside the integral. So if I can add the function epsilon to g, then I reach the contradiction, right? Because then I really lift the g up. And if this is always bigger than or equal to 0, then I'm still staying in this S that I define. The point here now is that, okay, I know if I throw in the big X, then I get a number here which is strictly bigger than 0. That's how I chose my epsilon. But I don't know that that is true for all subsets A. So here, truly now I can have a signed measure. And here's where it gets super nice. Then we use the Hahn decomposition theory to provide us a positive subset. And that's going to be, then we can do, instead of adding epsilon like uniformly, just lifting g up, we're just going to add it on the positive subset, and then things are going to work out. Nice. So,
all right, so I thought I'll add a bit of details here to describe the difficulty. So let's say that nu is f times the mu. So, we have this form that we're trying to prove. It's just that let's then assume that our function g is actually strictly less than f, at least somewhere. So then g can look like this, and then it makes a dip, and then it's the same as f again. So that's our g. What we want then to produce a contradiction here is we want to add a bit to g and still keep this inequality that we have nu of a is always bigger than or equal to integral g plus this something here, the mu over a, right? So if nu is given like this difference here is the same as saying that f is bigger than or equal to g, right? So we have this, but then we say the inequality is strict somewhere. Okay, so then, the easiest thing you can add here is just take a small number, epsilon times the characteristic function, well, times 1, right? It's just that it might very well be that, like here and here, if we add a bit, let's change color. Now I'm just getting a function like this, right? And then I screwed it up because now here I'm too big and here I'm too big as well. So then I don't have this inequality any longer. So what is really, so we need to somehow identify this set here, right? Or some subset here of positive measure, and then just add on that set. Okay, so the question is then, how will you find it? And here's where the theorem gets really clever. So now or the proof gets really clever. So you find this new measure, which is, well, this guy, right? Minus this guy, minus integral over AG the mu. And then we do minus also epsilon times the characteristic, epsilon times 1. Well, yeah, so, okay, minus, okay, so, yeah, so we integrate the mu, so that's what we do, right? We integrate just a constant. So what happened now, okay, let me paint this again. Is, so the difference between F, what we have here, and G is like nothing up until this point, and then it is a bump, then it's 0 again, right? That's just F minus G. So if we now do F minus G minus our epsilon here, what we get is this. And now, as long as this epsilon is small enough that we still retain a positive part, which we have, that's how we design the argument that we get, then you see that, okay, how can I find this set P, or this set, let's call it E maybe in the proof, that I'm interested in? Well, this is now the set P when you use the, oh crap, okay, sorry about that. So this is the set P when you use the Hahn decomposition theorem on this big guy. And then you see that, okay, if we go back here, if I take, now I do the Hahn decomposition theorem on this fellow, I use this as my E or P or whatever, and then I just add here, then I'm still under my F. Beautiful, right?
Omega is now assigned a measure. And by how I chose my epsilon, I have omega of x bigger than 0. So then Hahn, there exists some set P which is positive for omega. Okay, and now consider here instead mu of a to be equal to integral over, minus integral over a g plus epsilon characteristic function of p d mu. So, I mean, a here I can split it up in a part which is not in p, and then I know that, okay, let's do this. So, well, what I want to say is that we always have that this is bigger than or equal to 0. And how do we see that? Well, clearly, if I do here intersection with P and here intersection with P, now this is just omega of A intersection P is a subset of P, right? So then it's a positive or less non-negative number. Okay, and then if I add the P's outside of that, then this integral that I added here doesn't do anything. So for any, I have always mu of A intersect the negative set minus integral A intersect the negative set G the mu. That's also bigger than or equal to 0 because, yeah, this was, I mean, before we added him, we always had that, right? Now, if I add these two up, then I see that this can remove this intersection with n here and here. So I just have that. Okay, so let's take this away. So at the end of the day, I know that this is bigger than or equal to 0 for all subsets A. Okay, but this means then that G plus epsilon characteristic function of P is in S. And I still haven't used that nu is absolutely continuous. Why? Because this set P could, if it has measure 0 for mu, then I didn't reach a contradiction, right? I really need to make something bigger here. So, where was it we used Han? Han also says that the positive subset, you know, we had that this was a, when we applied this to X, then we got a positive number. Okay, so that's what I have here. And then Han says that also this is positive. Now, omega is absolutely continuous with respect to nu and G. Sorry, with nu and also this one is trivially absolutely continuous. So if omega of P is bigger than or equal to 0, then nu of P is bigger than or equal to 0, and then mu of P has to be bigger than or equal to 0, because otherwise that would contradict the absolute continuity. If I integrate this guy, which I know is in S, then here I get L, as we established already, and then plus epsilon times a non-zero number. And that is the contradiction, because now L was the supreme one, right? So this, you can't add something to it from coming from a function in S. So, yeah, fantastic proof. Requires to think about many times. So now, yeah, so this function G is defined. Well, I mean, if you have two different representatives, they're equal almost everywhere. So it's not a unique function, but up to almost everywhere equality it is. So it has a notation. We call it, we use the same notation as for derivatives. And the reason why we do that will become clear in chapter 4.4, where we do the analogy here, or the application to integration on the real line, the fundamental theorem of calculus. So for now, this is just notation. Hello. Okay, so if a measure is not absolutely continuous, then what should we call those? You know, clearly there are examples like you take just let your mu equal to lambda plus delta 0. Well, actually, let me call this nu, and then you have mu is just equal to lambda. Then somehow naturally this piece here is, I mean, it's absolutely continuous, right? And then this guy is definitely not. It's a point mass. So how do we? So this is an example. I mean, it has some part of it. It's absolutely continuous, and some part of it is not. So we want to talk about those guys that are, you know, absolutely no possible way absolutely continuous. What should we call those? So we know now that, you know, if we have mu of A, if that implies that mu of A is equal to 0, sorry, mu of A being equal to 0, if that implies that, then it's absolutely continuous, and we can write, you know, this is function f. such that we can write this, at least under certain assumptions. So this is sigma finite and whatever. But okay, so what should be then the how do we characterize like these guys who are definitely not of this type? Well, maybe this. Nah, that's not good enough. We can't have a measure which is always non-zero just because the first guy is zero. So let's talk about non-negative measures here to begin with. But this is almost where we are. So if there exists a measure A where mu of A is zero and this guy is positive. So this says that, okay, the mass of A nu is in A and A has a small measure. But then you want to say that all of nu is sitting there. So you also want to have that mu of A, the complement, is equal to zero. And then you want this to be positive. Otherwise, if this would be equal to zero and then it's zero here as well, then mu is identically zero, so we get a silly example. But basically, this is what we want. So you have some set A such that here all of mu lives here. So mu here has nothing, but all of mu lives here, and here, there's nothing of mu out in this piece. Then we call these guys mutually singular. So if there exists such an A, then mu and mu are called mutually singular. Okay? A good example is with the Hahn decomposition theory. If this is the positive set and this is the negative set, then mu plus, it lives here and it gives zero measure here. Mu minus gives non-zero value here and zero value over here. So actually these guys are mutually singular. So we have, this is denoted mu perpendicular to mu. So as an example then, in the Hahn decomposition theory, the positive and negative parts are mutually singular. Another example, the Lebesgue measure is mutually singular with respect to Dirac measure at zero, or for that matter, let's take the sum of the Dirac measure at 0 and 1. Yeah? Because then you just take A to be equal to the sets, the points 0 and 1. So the Lebesgue measure of that is 0. And this measure, if we call it nu, is 0 on the complement. And yeah, that's basically what we need. Okay? Just like with the Hahn decomposition theory, this we can always subtract and add sets of measure 0 as long as they have 0 measure for both of these guys, right? So the rational numbers could also be a candidate for A, because all of this measure nu, as is mass concentrated in the rational numbers, because 0 and 1 are rational, and the Lebesgue measure of the rationals is 0. Likewise, the nu measure of the irrationals is 0. So they are mutually singular either with this one or with that one. It doesn't matter. So anytime there's ambiguity of how to pick A, it's only on sets which are 0 measure now with respect to both mu and nu. So notice that to talk about mutually singular, you always need two measures, mu and the nu. But here the role is kind of balanced, yeah? So mu is mutually singular with respect to nu, if and only if nu is mutually singular with respect to mu. You could, you know, flip the order here, which is not at all the case for absolute continuity, which also requires two measure, but there's an asymmetry in the definition. Of course, there are sets. So there are measures mu and mu which are absolutely continuous with respect to each other in both ways. Then you just need to have this function to be non-zero almost everywhere, let's say everywhere. Then you can flip it around. Just then the other measure you just get by integrating the inverse function. Okay, again in the non-negative case, I'm not dealing with signed measures yet. Now, so of course, in order for this to have a meaning, so when we talk about sets of measures zero, I mean, you know, something that happens almost everywhere, then, you know, that's something that happens on a set of measures zero. It means that, like, okay, we have in our mind that sets of measures zero are small. Now, if you have a signed measure, that's no longer true, right? A signed measure, you always have a positive part and a negative part. And as long as this one and this one are equally big, the measure of the full space could be zero, but that doesn't mean that the full space is, you know, negligible. It's not small. So when we want to talk about negligible sets in the context of a signed measure, what we do is we replace the measure for the variation, which we know in terms of the Hahn decomposition theory is the sum instead of the difference. And then all of these problems disappear. So I'm not going to mess up my blackboard by writing it, but mu and nu are mutually singular. We still denote it like this. If this is true, this line is true, you just put here, okay, the variation instead. Okay, first question, is it so that we always have, so how can we construct a bit more interesting measures that are singular with respect to Lebesgue measure? Is it always like sums of Dirac? Of course, you can take an infinite sum of Diracs. You can take counting measure on the rationals. That would be mutually singular with respect to lambda. But can we get something like, okay, can we get something which is mutually singular but gives zero measure to every point? Think about that for a while. If something has, so you have the real line. Now you need some sort of thin set like the rationals. So it won't be too many points here. And then if every point in this kind of thin set has measure zero, shouldn't then the full measure be also zero? The answer is no. This is very curious. So remember this, remember the Cantor set? Yes, we remove a third, so it's 0 to 1. We removed the third, and then we said, well, here our function is going to be a half. Then we removed here and here. We said here the function is a quarter, and here it's 3/4, and so on. And like that, we managed to construct some sort of function that was increasing continuous, going from 0 to 1, but it somehow jumps up without, I mean, so the derivative is 0 on the complement of the Cantor set, so it's 0 almost everywhere, and yet it manages to increase without having jump discontinuities. Now, this is just bizarre. So here we can construct, so let's call this guy, this is the Cantor function. You revisit it in 1.3 something, in section 1.3, they introduced this guy. It turns out, okay, so f of x, you know, it's just a value here. So there exists, okay, a new example here. So there exists a measure mu such that mu of the infinite interval up to x is always equal to f of x, okay? But this means that if I have a particular point here, let's call it A, well then, mu of A minus epsilon, comma A, or let's, instead of epsilon, let's do 1 over n. That will then be, f of A minus 1 over n minus f of A, right? Sorry, of course, it should be the other way around. So here you just have f of A, and here you have minus f of A minus. Now it's correct. So if I move this to the other side, then I get, yeah, and then I use just additivity of my measure mu, then I get the full interval up to A, and yeah, so that's easy to verify. And now you take a limit here as n goes to infinity. Well, by this proposition 1.2.5 or 6, you just get the measure mu at the point A. But this is a continuous function, so this is always equal to 0. So here we have a measure that gives 0 to any point, and yet somehow it only lives on the Cantor set. Because clearly outside the Cantor set nothing happens, the function is flat. So there the measure has no mass. But the Cantor set has measure 0, right? So like this, we construct an example which is singular with respect to Lebesgue measure, but has no point masses. Very exciting stuff, very counterintuitive. Anyways, and now you go like, okay, but you have to tell me more about this construction. Well, this construction was done in 138, and we skipped it when we did the basic course. But this is basically a taster for how you do what's called Lebesgue-Stieltjes integrals. And we're going to go through all of that in chapter 4.4. So it comes after this lecture. And because of that, we're going to go back and look at how you can construct functions from measures and vice versa. If you have a measure, if you have a measure, it's easy to construct a function like this. This is the definition, but if you have a function, it's not clear how to construct your measure. So we're going to revisit that next time. So for now, just take the existence of this guy for granted and go like, wow, cool. So this is now where we're coming up to this, masterpiece generalization of the fundamental theorem of analysis as well. Okay, but all of that next time. So this is for now just a curious example. So what do we want to say about these singular measures except that they exist? Well, we want to get back to this guy here. It's not absolutely continuous. It's not singular with respect to Lebesgue measure. It's neither, right? So it has a piece which is absolutely continuous. It has a piece which is singular. And wouldn't it be nice if all measures had this property that we could just divide them into two? And for a change, our desires is fulfilled without any complications. Of the key theorem of today and the key theorem of section 4.3. So it is called Lebesgue decomposition theory. So we want mu to be a non-negative measure. Probably it needs to be sigma finite as well. No, okay, so mu can be, he says positive measures. I get lost in this. Sometimes you're supposed to say non-negative, sometimes not. Okay, anyways. So positive measure and then no restriction on it. Doesn't need to be sigma finite or whatever. But the other guy knew he should be sigma finite unless it is finite signed or complex, because then it's more than sigma finite and it's finite. At least the parts you get from the Jordan decomposition theory. So yeah, anyways, I'm not going to write up all this. Let me just state this for the finite non-negative case, right? And then you read the book for the rest. So mu and mu are positive and finite measures on some measure space X, L, and yeah. Then, so there exists an absolutely continuous measure mu A. There exists a singular measure with respect to mu, mutually singular. Singular, sometimes you say mutually singular too. But just underline that this is reflexive, but most of the time you just say he's singular with respect to mu. All right, such that the original guy is the sum of these two. Ta-da! And the proof, compared to the beauties of Hahn and Radon-Nikodym, is actually pretty straightforward. So, we need now to find a set where the singular part of mu lives. So we need a set of measure 0, mu measure 0, but where all the mass of nu is somehow concentrated. Yeah, mass I use just in an intuitive way. It's not a strict definition when I say mass. And what we're going to do then is we define L to be equal to the supremum of mu of A for all subsets A in our sigma algebra, such that mu of A is equal to 0. Very natural definition, right? Or thing to look at. We're interested in sets where this guy is big and that a guy is 0. So we look at this. Okay, as usual, we don't know that L is attained, but we can always find a sequence of sets AN like this, such that the limit of this guy here is that. And then this set A, which we want to construct, where nu is concentrated, I just do without any complications an infinite sum. Sorry, an infinite union. All right. So then we know if you take an infinite union of sets which have measure 0, they again have measure 0, so mu of A equals to 0 is immediate. Okay, so then we have our set here X. Now we got some set A, which is a small measure. So now let's say that mu is not mutually singular. That would mean, also, let's say that this set A is not such that it makes, mu and mu mutually singular, so that we know already that mu has measure 0 here. So then we just want to show that mu has measure 0 on the outside. So let's say there exists some set E here. So if this set E then again has measure 0, doesn't look like that in my picture, but let's say it has, and this is bigger than 0, well, then you just do mu of A union E. Oh, that's L plus mu of E. So This is a contradiction. That's not going to happen. Yeah, because we cannot get bigger than L. That's how we constructed L, right? So, okay, so E didn't exist. So this means that what we have now is that mu of A is equal to 0. Now we define mu, the singular part. We define it on some arbitrary set E by just doing mu of E intersected with A. Right, that's our singular part. Now by how it's constructed, it lives on A. The set mu can have still mass out here, right? But it can't have any mass on something which has measure 0. So what we get after doing that definition is that the singular part of mu doesn't live outside of A, because we define it to not live outside of A, right? So now these two are mutually singular. That's fine. That's not difficult. Now the only thing that remains is to prove that what's left of nu is absolutely continuous, because otherwise this is not worth much, right? So define nu of A to be equal to nu minus nu s, which then of course is just nu of, now if I insert the set E here, then I just do the intersection with the complement of A. Right, but we just said that as long as, now we're back here again, right? If E lives in the complement of A, so once you do the intersection, you have something that lives in the complement. So if you have something here and it has positive measure, then it can't have 0 measure for mu, right? We just showed that that was a contradiction. So somehow, yeah, it's immediate that so by the above, mu A of E is equal to 0 if mu of E is equal to 0, i.e. mu A is absolutely continuous with respect to mu. And that's the Lebesgue decomposition theory. I always say that then extensions are boring. I'm not going to bother with them. Maybe one time I can actually bother with it. So nowhere here did we use that mu was finite, so we can just throw that away immediately. We did use that mu is a finite measure, and where did we use that? Probably on a few cases, like L should be a finite number, for example. Okay, so then if we have a signed measure, then really you just do the Lebesgue decomposition on mu plus and the Lebesgue decomposition on mu minus, you add up. This is nothing difficult. But what about a sigma finite? Nu, well, in that case, you have your big space X. And what does it mean to be sigma finite? It means that I can take a smaller one, let's call it X1, a slightly bigger one, let's call it X2, and so on, such that the infinite union here is equal to my X, and every time nu, which is now a non-negative measure, I stick with my, I call them non-negative all the time, so I'm not going to change and call them positive, just because the book wrote it. So nu here is non-negative. Okay, so it's a finite measure for each x1, x2, x3, and so on, and these ones are growing. So then what we proved above shows that nu restricted to any xn, then we call that nu n. Now we do the Lebesgue decomposition theorem there, and it tells us that there is an absolutely continuous part and a singular part. Wait, there's an even better way of doing this. Let's let mu n be equal to nu restricted to the rings, yeah? Where mu1 is equal to nu of, we're just restricted to x1. So you start here with this chunk and then you do the rings. Now they are disjoint. So then what we will do now is we'll define mu absolutely continuous as the infinite sum of mu n absolutely continuous. We define mu singular as the infinite sum of the singular guys. And now, since measures are countably additive, it's really easy to see that since each one of these mu n's are singular with respect to n, then the infinite sum will be as well. Same here, if it's absolutely continuous, each guy in this sum, then the infinite sum is absolutely continuous as well. This is really peanuts to check. And then, by the way we constructed this, of course, we have that mu is equal to the infinite sum of the mu n's, which is infinite sum mu n a plus mu n s, and now you just look this up. And then by our definition, this is mu a plus mu s. All right, so you see this just becomes boring, yada, yada, yada. I don't know if there's some tiny complication I overlooked. If it is, anyways, you have the proof here in 4.3. They go through the details. Good, and that's that. So today we covered 4.2 and 4.3. Next time we will do 4.4.